Hi Year 11 and welcome to the first in a series of videos for the topic Combinatorics. In this lesson we're going to look at counting techniques, factorial notation, duplicates, and then revise theoretical probability. So let's start with an example. In a set of 3 lights, the light bulb can either be on or off. How many different combinations are there? Because there's only 3 different light bulbs and 2 possibilities, it's not very much work to actually list all the different combinations, and there are 8. But you can probably see that if we got more light bulbs or we had different possibilities, it could soon get out of hand. We need a simpler way to do this. Which leads us to the fundamental theorem of counting, and it says if one event can happen in P different ways and another event can happen in Q different ways, the 2 events can happen in P times Q different ways. So let's return to our question. How many different combinations are there? Well, the first light bulb has 2 possibilities, on, off. So does the second one, so does the third one. So we're going to do 2 times 2 times 2, which is 8. Okay, let's have a look at a couple of examples. Joe travels from Mumbai to Fiji via Hong Kong and Sydney. If there are 5 flights from Mumbai to Hong Kong, and 4 flights from Hong Kong to Sydney and 2 flights from Sydney to Fiji, how many different journeys can be made? So let's just draw up a quick diagram. I'm going Mumbai through to Hong Kong, and then through to Sydney, and then through to Fiji. There are 5 flights Mumbai to Hong Kong, 4 flights Hong Kong to Sydney, and 2 flights Sydney to Fiji, and we're just going to multiply those possibilities. And so there are 40 different journeys. Here's another example. Now back in the 1900s, little girls used to play with cardboard dolls, and what you would do was cut out the dresses or the coats and the hats, and you could dress your doll in different outfits. And we can see here that we've got 2 coats, 2 dresses, and 3 hats. So how many different outfits are possible? We would go 2 times 2 times 3, which is 12. And example 3, how many possible number plates can be printed with the format letter, 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 digit, digit, digit? Well, there's 26 possibilities for each of these letters. And how many digits are there? We have to include the 0. So 0 through to 9, there are 10 digits. So the number of possible number plates must be 26 times 26 times 26 times 10 times 10 times 10. Or we can write it in index notation, 26 cubed times 10 cubed. It gives us 17,576,000. Now that previous question is what we call with replacement because duplicates were allowed. For example, we could have had the number plate AAA000, but quite often we're asked questions without replacement, like this one. 5 cards are dealt in order from a standard pack of 52 cards. How many arrangements are possible? Well, if you think about it, there are 52 different possibilities for the first card, and when we've chosen the first card, there are only 51 cards left. And then for the third card would be 50, fourth card would be 49, and then the 5th card would be 48. And so the number of different arrangements are 311,875,200. Another really good example is a horse race because the same horse can't finish first and second. So it's naturally without replacement. How many ways can the horses finish in a 12-horse race? Well, there's 12 horses that can finish first, and then 11 that can finish second, and then 10, and then 9, then 8, blah, 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 all the way down to 1. Altogether 479,001,600. But thank goodness there is an easier way. Let me introduce you to factorial notation. The factorial of a positive integer n is the product of all of the integers less than and equal to n. So n factorial is n multiplied by n minus 1 multiplied by n minus 2 all the way down till we get to 2 times 1. And this is the notation here, the exclamation mark. So our answer to the previous question was 12 factorial. And luckily for us, there is a factorial button on the calculator. It's just here. So all we have to do is 12 and then press that button and we're going to get our answer straight away. We don't have to go 12 times 11 times 10, etc., etc. Here's another example. The letters A, B, C, D, and E are each written on a card and then the cards are dealt in a random order. How many different orders are there? So this would be 5 factorial. When we put that in the calculator, we get 120. Let's move on to duplicates. In how many ways can the letters wool be arranged? Now at first glance it might seem like there's 4 factorial, 4 times 3 times 2 times 1. But if I actually list them all out, you'll see that we've got duplicates. This word here is actually the same as this one. I've coloured one of the O's a different colour so you can see, but in reality the O's are identical. So we've got twice as many arrangements as we need. In fact, the number of arrangements will be 4 factorial, the number of ways that you can arrange the letters, and then we divide by any duplicates. So 2 factorial is the number of ways the O's can be arranged. So our answer is 12. Here's another example. In how many ways can the letters mathematics be arranged? So if we count up all these letters, we'll find that there are 11 of them. So we want to divide 11 factorial by all the duplicates. And there are 3 duplicates. There's 2 M's, 2 A's, and 2 T's. So we do 11 factorial divided by 2 factorial times 2 factorial times 2 factorial. Now you might be thinking, why do we need the factorial here? Because 2 factorial is just 2. And that's actually okay if there's just 2, but if you've got 3 letters the same, then there are 3 factorial ways to arrange them. So I would encourage you to keep this factorial notation even for the 2. The answer is 1,989,600. And lastly, how many ways can we arrange the letters isosceles? So this time we have 9 letters, we have 3 S's and 2 E's. So our answer is 9 factorial divided by 2 factorial and 3 factorial, which is 30,240. Now let's just review theoretical probability. Recall that the formula for the probability of an event E occurring, yes, this is the notation, probability that E occurs, is equal to the number of ways that E can occur divided by the total number of possible outcomes. We can use this set notation if we want to. This means number of elements in the set E and number of elements in the sample space S. Now let's return to this question and do some probabilities. Calculate the probability that we get A, B, C, D, E. Well, how many ways can that happen? Just 1. So the probability is 1 out of 120. What's the probability that the A will be first? Don't overcomplicate this. We actually don't care about the B, C, D, and E. We only want to know this position. What's the probability that A will appear here? 1 out of 5. And this question, what's the probability the vowels are together? Now I'm actually going to leave you to work on this question. I'm going to answer this in the next lesson. I just want to finish by talking about 0 factorial because curiously 0 factorial is equal to 1. And it doesn't make a lot of sense, does it? If anything, you would think 0 factorial would be equal to 0. But one way you can figure it out is just to look at the pattern. Now 4 factorial is equal to 24, 3 factorial is equal to 6, 2 factorial is equal to 2, 1 factorial is equal to 1. So what's 0 factorial equal to? What are we doing here? 24 divided by 4 gives us 6, divided by 3 gives us 2, divided by 2 gives us 1, divided by 1 gives us 1. Okay, that's it for this lesson. In our next lesson, we're going to look at the pigeonhole principle.